Okay, so I suppose I'll start. So, good evening. I welcome you to this problem solving and live interaction session for this course on experimental stress analysis that is offered by Professor K. Ramesh in the Swayam portal. So, the idea, I'll just run you through the idea behind these sessions. So, weekly we will be having these sessions at the same time from 6 to 8 on Mondays throughout this semester till the course is over. So the idea is that I'll be solving some sample problems from whatever the contents are for that specific week. And then whatever doubts that come as a result of that solving, participants are free to ask and I'll try to answer them. Granted that I might not be able to answer each and every question that is posed readily. If that be the case, I'll take note of those questions and try to address them in the next subsequent sessions. And in addition to that, since you are part of the course, so I would suggest that everyone please join the forum, the discussion forum of this course. If you go to the Swayam portal, there'll be an Ask a Question uh, tab. You can just click, it'll take you to a Google group, which is meant for discussions. So you can join that group. Even if you don't have a question, other people who are asking questions, and we will try to answer them. So you can at least get a feedback, a digest of those answers, which will lead to a better learning experience, is our anticipation. And as soon as these sessions are over, preferably on the same day, I'll also try to upload the session that I'm conducting right now. I'm recording them, so I'll also try to upload them somewhere. And the links to those videos, as well as the writing pad which I'm using where I'll be solving, these two will also be made available in the appropriate time by the Swayam team. And it will reflect in the course page itself. Wherever we see on the left side, we see week one, week two, there on the bottom, preferably very soon, they'll upload the videos and these notes there, so you can refer to them. And other than that, if you have any questions during the week, that you can just collate and try to ask it in the forum or in these live sessions. So as I said, since two people have joined additionally now, I'll just briefly repeat that I'll be solving questions and you can pose your questions that you have on them. If I'm trying to, if I can, I'll answer them right away. If I'm unable to answer them right away, still I'll take a note of them and try to address it in the subsequent sessions. So this session, it will have the same Google Meet link and this will be conducted throughout the course of this semester on Mondays, 6 to 8 p.m. So I hope that that is clear. So is there any question as of from the participants? If there are, I'm happy to take them now. Any? Yeah. Yes. Okay. 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 Yes. Yeah. Yeah. Yes. Yeah. Okay. Okay. That I'll come to that. Anyway, during the course that I'm solving this session, one of the questions is about a spanner. So, if it's okay with you, I'll try to take it up there. I'll give you a brief of how that was captured. And then when we go to the details in the method, because right now we are discussing week one, which is essentially to do with the preliminaries and just a basic introduction to the methods. And as we go during in the course of in due course of time, we will also come to that method. That method is basically photoelasticity. We have used transmission photoelasticity to capture that. So the nuances of that and how that was captured, that also I'll try to address. In that is, I'll try to address that in steps. I hope that is okay with you. Yeah, yeah. Okay. So with that preamble, so I suppose I'll get started. So uh, I'm sorry, I forgot to introduce myself. My name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics and Biomedical Engineering, and I'm pursuing my PhD under the same professor who is offering this very course, Professor K. Ramesh. And my co-guide is Professor U. Saravanan from the Civil Engineering Department. So with that, let me get started. So let us look at the first question. So it says, can you get a solution for a rectangular bar subjected to torsion from strength of materials approach? The question says, yes. Yes, the solution is same as a beam under bending. No, because plane sections do not remain plane before and after loading. No, because rectangular bar cannot be subjected to torsion. So granted, many may know the answer. I'll just try to explain what we are trying to ask. So essentially, we have a bar like that. So what is being asked is, torsion we know can be represented using a double-headed arrow or like that. So essentially, we are trying to twist the bar. So we are applying torsion on it. So from strength of materials, what is it that we know? We basically make an assumption on the displacement and verify that with certain experiments if that is indeed holding. If that is holding, it helps us to get to the actual stress analysis without having to solve differential equations. So here the basic assumption is that the plane sections remain plane before and after loading. So we have plane sections remain plane before and after loading. So what does this basically imply? If this same beam, let us say this rectangular bar, if I was to bend this by applying two moments at the ends, that is if I take the same thing and instead of these, if I were to apply couples at the end, then we know that this is subjected to pure bending. What is meant by pure bending? Essentially, there is a constant bending moment, so there is no shear in this beam. In such a case, when we look at the deformed shape of this, if I were to just take this face, if I were to just take this front face and view it as a two-dimensional this thing, the deformed shape will be something like that. I'll just roughly draw this. Deformed shape will be something like that. So if I were to take a plane like that, the plane would be deformed to a plane like that. So whatever be the neutral axis that I have, the angle that the plane is making will be preserved. So it will still be normal. So that is the essence of plane sections remaining plane. Whereas if we were to look at the case of torsion, it is only this assumption of plane sections remaining plane before and after loading only holds in the case of a circular shaft. And this can be shown by experiments also. So there is a course on strength of materials offered by Professor K. Ramesh, newly launched course that is also available on YouTube as well as Swayam portal. So interested people can just watch a lecture on torsion, thought experiments, something, the name goes something like that. So that actually shows an experiment conducted on a shaft where we are able to see that the plane section indeed remain plane even after a torque is applied, even when it twists. Whereas that is not the case when we have a rectangular shaft. So what happens here is essentially we will be seeing a line that is drawn like that will deviate like this. So it will no longer remain straight. So essentially we will have some out of plane displacement. If this is the plane, if that is the plane, we will have some out of plane displacements, which is known as warping. So rectangular shafts are subjected to warping. Does that mean that we cannot get the solution for rectangular shaft subjected to torsion? It is not so. We can get it provided we go approach it from the stress potential, that is the theory of elasticity approach, rather than the strength of materials approach. So from strength of material approach, this problem is consciously avoided. When we talk about torsion in strength of material, we directly start with the circular shaft and we end it there. We don't discuss about other shapes. A circle, and at best we will discuss about hollow sections, that is axisymmetric, but we don't discuss about rectangles and square shafts, whereas these are also used in practice. So the solution for this can be obtained using theory of elasticity approach. So essentially plane sections do not remain plane in this case, which is why we cannot get, because plane sections do not remain plane. Fourth option doesn't make, essentially we cannot constrain a bar from being subjected to any type of load, depends on where the component is placed. So this is not in our hands, but whether we can analyze that using our theory is the essence of this question. So I suppose that that is clear. Should you have any questions midway, you please feel free to stop me and ask. In the meantime, I'll move on. So I hope that there are no questions and this is clear. Should there be questions, please feel free to ask. Okay. And before I proceed, I just wanted to make sure uh, if the speed and the articulation is fine with you, or should I go slower? And if there is a, because I'm conversant in three languages, I can, I'll try to explain it mostly in English. But if there is a need for you, for if you want me to explain that in Hindi or Tamil, I can do that as well, because these are the only two languages apart from English that I know. So I can try to accommodate that in bits and pieces here and there if need be. That is, if you need that to be. Anyway, so I'll proceed with the next question. So the next question says displacement is represented as a number, a vector, a tensor, or can be any of the above. So which one do you think is the answer? So essentially, what do we mean by a number and a tensor and a vector is that any quantity, any mechanical quantity that we are taking, if we have a boundary value problem, let us say we have a domain. At that domain, we have some point, and this is subjected to some load like that. Yeah, yeah. So essentially, displacement is a vector, but I'll just go through a small brief on what a tensor is and what a scalar number essentially represents. So at this point, if I were to take this point and if I were to zoom it in, I'm only talking about the in-plane response right now. I'm not talking about the out-of-plane response. So we can see that we essentially have four planes. This being plane number 1, plane number 2, plane number 3, and plane number 4. So at each of these planes, essentially I have some sort of traction that is acting. So when it is dependent on the plane as well as the direction of the force that is applied, it has a it has dependence on two directions. So that is why it is called a second order tensor. So stress and strain essentially are second order tensors. Whereas displacement has only three components. Anywhere in three-dimensional space, we can characterize displacement. This point moves to here, we can characterize that by the three displacement components. Essentially, this is u, this is v, and w. Since we are talking about the same plane, the displacement along the w, that is the out of plane displacement, would be 0. So that is why displacement is represented as a vector. So in any problem, in any mechanical problem, we generally have, the idea is to relate forces, so to displacements. In general, if we idealize the body as rigid, in engineering mechanics, we have seen how these two are related. In the case of engineering mechanics, when we idealize the body as rigid, whatever force we apply, it creates an acceleration. So acceleration is nothing but the second derivative of the displacement. So F equal to mu, if I call this u, so it is mu, second derivative of the displacement. That is how this is related. Whereas when we talk about deformable bodies, in reality, all bodies are deformable. So in such a case, we need to go to strains. From there, we need to relate them to stresses. And this stress is at a point. So as a whole, we need to integrate it throughout the domain of the body in order to get to forces. So this is the basic route in which we go. Now this, from displacements getting to strains, this is nothing but our strain. This is nothing but our stress, and that is forces. So from displacements, there are basically, displacement is a vector. So we have three independent displacement components. Whereas strain is a tensor of rank 2. So essentially this has 6 independent components. That is a strain tensor. When we represent that, let us say we are representing that in the XYZ coordinate system. So we know this is epsilon XX, epsilon XY, YY, epsilon ZZ, and then XY, XZ, and so on. But the strain tensor is symmetric. So essentially we have to determine only this triangle because the other end is symmetric about the diagonal. That is why we say there are only 6 components that are independent. So this will be YZ, XZ, YZ. So these are the 6 strain components. So from 3 displacement component, we get to 6 strain components, which are related using the material to get 6 stress components, which are again integrated in order to get forces. And force again is a vector. So this again has 3 independent components. So anywhere in theory of elasticity or wherever that is, we will be essentially moving either this way or this way. That is from stresses, we'll go to strains and then integrate to get to displacements, or we'll measure the displacement, take its gradient, we'll get to strains, convert them to stresses using the material properties, and then integrate to get to the forces. And essentially, we have to do force balance. So that is the basic idea. So I hope that is clear. So displacement, as someone had pointed out correctly, displacement is a vector quantity. So if there are any questions, please feel free to ask. Yeah, yeah, I just gave, right? So the thing is, at a plane, whatever quantity that is under consideration, if it has a dependence on the plane as well as the direction in which that is applied. For example, if we take this plane can have forces applied in infinite directions. So there is one directional dependence that is characterized by this very plane. What is a plane characterized by? How do you identify any plane? We identify by its outward normal. And then we have a force that is applied on this plane, which can be in any arbitrary direction. Let us say that is the direction. So this is direction number 1. This is direction number 2. And then we have a magnitude associated with that force that is being applied. So a single magnitude and then a directional dependence on a bidirectional dependence. That is two directions it is dependent on. So that is why we are able to see that there are two subscripts here, right? One represents the plane on which we are considering it, and the other represents the direction in which the quantity is going. So these two, when they come into the dependence, it is called a second order tensor. Is that clear? Yeah. What is the rank? Yeah. Yeah, rank is, as I said, the two directions that are there, right? First is the direction in which the force is applied, and and the plane that we are considering, the direction that is characterizing the outward normal. So these are the two. So this is the rank. One, yes, yes, you can say that because it has a single directional dependence. But that goes into more generalizing the theory. Actually, any tensor is defined only by how it acts upon a vector. So when a vector acts upon a vector, if we define it from the tensor's perspective, it can give you either a tensor or a scalar, either a second order tensor or a scalar. I hope that is clear. Yeah, okay. So let us get to the next question. So this says a closed form solution is which of the following? The first option is the solution obtained close to the real solution, solution obtained at every point in the model, solution obtained near to the field of interest, solution obtained at the point of interest. So if we see, essentially, if we have a body and then it is subjected to some forces, it is constrained also, maybe at some point. So if by analytical means, if what is our interest? Essentially, we want to, our interest in stress analysis is to compute, is to be able to compute displacements, strains, and stresses. So in any problem, if we are able to compute these three at every point in the model domain, if this is the model domain, at every point, given any point, I can get an expression. Let us say if this is x, this is y, and then we have z. For example, if we take the XYZ coordinate system, in this body subjected to a particular kind of loading and support constraints, given the location, given the coordinate of any point, any material point in this body, if I'm able to get all of these quantities, it is called a closed form solution. So closed form solutions essentially, as it is said in the lecture also, it is a luxury to get. Not all problems have closed form solutions. So our first attempt is the closed form solution. If we can get that by any means, we go about doing that. If that is not possible, then we make certain assumptions uh, which which only outplay the dominant behavior. For example, in the case of bending, we know that it is applicable for a pure bending case. That is, there should be no shear. If there is shear, how dominant is the shear? If it is not dominant, then we may as well approximately consider it. Sir, is this session available offline? I don't have proper connection right now. Yeah, this session I'm recording it and I'll be uploading it. Uh, and the links to that recording will be shared in due course of time by the Swayam team. It'll appear in our course page to the left. If you see, there is week 1, week 2, and all that. So on the bottom there will be some live session, something like that. There will be a link created soon, if it is not already there. There, I'll be uploading the recording for this session as well as the notes on which I'm writing. So you can refer to them if the connection problem is persisting. I hope that is clear. Okay, thank you. Yeah, so as I was saying, that we try to look at the dominant aspect to the problem and try to make certain assumptions and arrive at some closed form solutions. If in the case that also doesn't work, then we have to resort to a near field solution. For example, if there was a crack here, if there was a crack in this body, there is an entire subject on this called fracture mechanics. So we try to make certain assumptions and try to derive solutions, in which case we will have near field solutions. So our assumptions are only valid near the tip of the crack and not very far away. To cite another example, if we take a plate and if we pull this, we know that we have closed form solution at every point. Whereas if a small discontinuity were to be introduced into the plate, then we no longer have a closed form solution. Then we are looking only at a near field solution. So that is how this goes. So solution at every point in the model is what is called as a closed form solution. Solution obtained close to the real one is nothing, as the name as the very definition suggests, it is a approximate solution. Solution obtained near to the field of interest. This is again some kind of approximation that we are making, and it is obtained at a point. Now this generally happens in experiments that there are certain techniques which are labeled appropriately as point by point technique. So we can only get one information at one point. If we have to get this information at another point, then we have to redo the experiment again. So that is essentially a point by point solution. So you can say in a way that the integration of this point by point technique towards in the entire domain of our interest being the material body is what gives us the closed form solution. So I hope that that is clear. So if there are any questions, you please feel free to ask. In the meantime, I'll move on. Okay. So which method is handy in solving problems involving arbitrary shaped boundaries such as a spanner tightening a nut? So as we saw, you can also see it here that you can see clearly that this is characterized by a particular curve. This may be an amalgamation of many curves. So in order to characterize this body, first, this is a boundary value problem because this has a fixed domain. So I have to define my boundary conditions over this domain. Now, can I characterize a coordinate system that can capture this entire curve? That is a big challenge. That is why we don't have closed form solutions for this, because it is not possible to capture the entire boundary, the entire domain using our normal analytical coordinates. So we have to resort to numerical modeling in order to do that, because the essence of numerical modeling is that it will divide this entire domain into very small parts. So for example, if I have to take a circle and if I have to make it only using triangles, if I'm constrained that I have to recreate the circle only using triangles, the first attempt I can make is like that. So for example, this will be my first attempt at that. So I can see that it is not representing the circle faithfully. It is just a crude approximation. So the next will be, let us say that I make it finer. Now this time I can have more points like these. So what this does is this makes it a little finer. I'll close with this. I won't draw all the possible combinations naturally. So if I were to close this, and let us say I remove this, now I can see that this is a much better approximation of the geometry, of the circular geometry. So like this, if I were to make this, the size of this triangle very, very narrow, then it is approximately approaching the actual boundary. So this is what numerical methods do. That is why we are able to solve complex boundaries using numerical techniques. So each and every one of these element has to be put in one form and solved in order to get the response of this actual circle under stress, under some mechanical stress. So that is how numerical approaches go about solving these. So the advantage is that any type of complex boundary, I can capture it and make the computer run simulations in order to run calculations in order to get my stresses. So that is why numerical techniques can handle this problem conveniently. The strength of material approach is anyway very limited even within its scope to very simple problems like a beam, rectangular beam under bending, a circular shaft under torsion. As we saw that even a rectangular shaft under torsion cannot be approached using the strength of material approach. So that also requires a theory of elasticity approach. And even with this, there are only a handful of problems that we can solve. Essentially, how theory of elasticity got developed is we formulated the solutions first using the stress potential approach, and then we have tried to fit it to different problems that were prevalent at that time. It's quite useful, but nonetheless, it is not exhaustive. In order to solve even a day-to-day problem like a spanner tightening a nut, we require numerical methods. Now, this being one constraint, if numerical methods can solve everything, that begs the question, then why at all do we need experiments? So numerical methods, we are only defining the boundary conditions and the geometry. So there is no confirmation that what we have defined is correct. It is not objective in that way. So any number of people can define it in any form, but ultimately there is only one response that needs to be captured. So how close we go towards that response is what the entire thing is about. So that is why it is desirable that when we make a numerical model for a complex problem, at least one case, one load case, if we were able to demonstrate that the response of that numerical model is similar to that observed in actual practice, then we are at least confident that whatever modeling we have done is faithfully capturing the phenomenon. Then what is the way to observe the actual response? That we do experiments on the actual prototype. Now, there are certain problems which are too big to be accommodated with the actual prototype. For example, some big ship, if there is in the shipping industry, if we want to do stress analysis, if we say that we want to test the numerical model, so we make an entire ship that is not a workable solution. So that is when we try to scale it down and create model experiments capturing the essence. So model experiment has a challenge that our loading jigs should be appropriately modeled in order to apply loads that are similar to the actual real life situation. So there are challenges at every step, but nonetheless, using all these wisely with the engineering acumen, we try to approach the problems and do our design evaluation. So I hope that is clear. If there are any questions, you please feel free to ask. Yeah, as for the one question that someone had asked about the spanner. So what we have done is we have the spanner like that. It's a crude. So as you can see in the lecture also, this is essentially transparent. It is not that only transparent models are stressed, but since we want to visualize that, we have tried to make it transparent using epoxy, and then when we tighten it, there are certain patterns that show up, but that patterns will not show unless you view it in one particular optics. So essentially, there is something called a polarizer, there is something called a quarter wave plate. These things will come in photoelasticity as we move towards the third or fourth week. So a normal spanner tightening a nut, a normal epoxy transparent spanner tightening a nut, if you view it you put a light behind it and you view it, you won't be able to see such patterns. But if you put something between the light source and the model, and similarly between your eye and the model, there are certain filters that we need to be put. And when they are put, whatever we capture, we are able to see that the patterns develop. And those patterns are essentially patterns of sigma 1 minus sigma 2. That is, for example, if we take this point, we know that that point can be represented as a stress cube. I'm talking only in two dimensions, so that stress cube degenerates to a square. In this case, we will have some sigma x, we'll have some sigma y, and then we will have some tau xy. This is in equilibrium. Yeah, so this is in equilibrium. So if we rotate it by some way, we can actually decompose these three components into just two stress components, namely our principal stresses sigma 1 and sigma 2. So that these contours essentially represent the constant principal stress difference, that is sigma 1 minus sigma 2 equal to some constant. So that is what those patterns represent. So that is how those patterns are captured. Is it clear, sir? Someone who had asked that question. Have I answered you at least partially? Yeah, yeah. So how this pattern get formed, that we will see as we go about in the course when we discuss the essence of how transmission photoelasticity works. Okay, so yeah, yeah. Okay, so let us look at this question. Refractive index is the ratio of velocity of light in velocity of light in vacuum to velocity of light in a specific medium, or is it medium by vacuum? Is it air by the specific medium? It is specific medium by the water. Naturally, it is not air or water because it's a standardized quantity, and these things are very much objective, non-objective, and dependent. So, refractive index is essentially defined as the speed of light in vacuum upon speed of light in the medium. So, why we are trying to see this? What has this has to do with our stress analysis? Is because our the technique of photoelasticity, it is based on the principle of stress induced by refringence. So when we talk about refractive index, we are of the notion that there is only one refractive index for one material. There are certain specific materials which, when they are stressed, they develop two refractive indices. So if there are two refractive indices, we can see that speed of light is constant. So naturally, that means that there are two different velocities of light that, through the same very medium when it is stressed. So what these two velocities bring about, what changes do they bring about, is what is what we are trying to study, and this manifests itself in the form of fringes. So that is why we are trying to insert certain things now so that we are familiar with these terms. When we go to the development of transmission photoelasticity, it will not be that hard for us to take it from there. So velocity of the light in vacuum to velocity of light in that specific medium is what is our refractive index. And refractive index is again a second order tensor. It has directional dependence on in two directions. One where the light is passing and one which plane are we considering. So we can see that refractive index is a second order tensor, stress is a second order tensor. So there seems to be some correlation that we can build in between these, which will be developed in when we go to week 3 or week 4, whenever we start the module on transmission photoelasticity. So I hope that that is clear. Okay, so let us look at this problem. The following fringe patterns are obtained using shearing interferometry. The patterns represent contours of what is what is asked. So in general, there are, when we go for experiments, each and every experiment has one specific physics that we are trying to exploit. Now, let us say that we want to do some experiment on a model. We are trying to study some problem, and we have made a model of that, and we are going to start with the experiment. But first, we have to ensure that our setup is correct. In order to do that, we need to do something called calibration of that setup. So for calibration is essentially seeing that the response from the experiment is same as that we anticipated. Now, for the unknown problem that we are trying to study, we don't know what to anticipate. So naturally, what we will do is, before we conduct for an unknown problem, we will conduct the experiment for a known problem. So there are certain benchmark known problems that have developed over time. From strength of material, it could be 4-point bending, pure bending, that is. From theory of elasticity, there is a disk under compression along the diameter. This is one of the problems. And then, so each and every problem has its own application. That is, each and every experimental method will employ one type of problem which will be standardized for that, which will be used to see if all the connections, all the setup is correct. Once we are confident that that is correct, then we will move on to conducting the actual test experiment, which we are trying to study. In that respect, now we saw that there are displacement components that we have to measure. There are strain components that we have to measure, as well as stress components that we have to measure. There is no experimental technique that can measure all of these. So every experimental technique is limited to measuring certain quantities out of these. Now when we are talking about in-plane response, that is, there is a disk which is subjected to this type of loading. Now, if I am considering this plane on which I am writing to be of my interest, whenever I am trying to do stress analysis using photoelasticity on that plane, the typical problem that we will take for calibration is the disk under diametral compression. Now, the displacement can be out of plane also. If I press this, actually displacement will also be along the z direction because of Poisson's effect. Now, if I have to measure out of plane displacement, then the staple problem that is taken is a clamped plate subjected to a point load. This load is actually applied into the plane of the paper. I hope you can visualize that. That is, if I were to see it like that, if I were to view it like this, what I will see is a plate that is clamped, which is loaded like this. And how will its deformed shape be? I know that slope here will be 0. Here, because it is symmetrically loaded, based on symmetry, I can say the maximum displacement will be at the center. It will again go back to 0. And because it's an axisymmetric problem, this curve will be symmetrical about the horizontal. So this happens to be the standard problem for the techniques that measure out of plane displacements. Now, for this problem of a clamped circular plate subjected to a central load, we have a closed form expression from theory of elasticity. If any of you have done a course on plates and shells, this will be the first problem you will solve when you go to polar coordinates from rectangular coordinates. So for this, we generally use the general Michel solution, and then we take advantage of the axisymmetric nature of the solution. So there is no angular dependence, there is only radial dependence. So like that, we will try to apply the boundary conditions and come up with the solution. Those solutions are already given in one of the lectures from the first three. If you see, those solutions are given. Now, those closed form solution, what does that mean? By taking this as the origin, by taking this as the origin, for any r, if I have a point here, if I have a point here, it is at a distance r. So at any r, I'll be able to get the out of plane displacement. So if I were to plot this using contours, let us say that I take this curve again. Let us say my curve is like that. If I have to plot this using contours, what is it that I'll do? I'll run lines. I'll run lines like that. At each and every such plane, whatever I'm seeing, I will try to club it. So when we actually, if you are interested, you can take the closed form solution that is given in the lecture, with the as a function of the radius r, and in MATLAB maybe you can just type in and try to plot the contours at different r. So what you will see is essentially concentric circles being a symmetric problem. What this represents is, this is for some displacement. Initially, there will be displacement equal to 0. Why displacement equal to 0? Because this is clamped around the border. Around the border, there is no out of plane displacement. Then there will be displacement equal to 1, 2. I'm just saying integers. It will be a continuous curve. So like that, it will be concentric circles. So such a curve is essentially the representation of out of plane displacement. Here we are able to see that this shows a peak here as well as a peak here, and then it shows a reversal. So why that happens is because this is clamped here at these ends, we have an inflection point here. So essentially, this is nothing but the slope. So this you can readily see in the lecture. This pattern is shown and it is already labeled as slope. I'm just trying to walk you through how this came about and to think about it when you look at the pattern as to what that might represent. Now, if I were to, let us say the disk, actually the disk would have been that way, clamped at the ends, and then at the center an out of plane load is applied. But I'm able to see that the response is actually this way. Here there seems to be no reversal. So it is safe to assume that the reversal is as a function of x. So this is nothing but slope. This is nothing but slope of the circular plate in x direction. Now because of axis symmetry, how will it look in the y direction? Yeah, so what I meant is when we look at this in the y direction, essentially these two eyes will appear there instead of horizontal. So that will be slope in the y direction. So, so this is nothing but our slope. Slope in the y direction. Out of plane displacement of a circular plate with a central load, we know that because of the axis symmetry, it has to be a symmetric pattern. This essentially is not a symmetric pattern about the vertical. So this definitely cannot be out of plane displacement because the problem is symmetric. So like that also you can start reasoning out. But I would encourage any of you who is interested to at least plot these patterns once and see. It is not very difficult. You already have the expression in MATLAB. You just have to type these out, MATLAB or Mathematica, whichever you are comfortable with. You just have to type these out and just plot the contours and see how they look. So when you have a visual appreciation of that, and then when you go do the experiment, it'll be more exciting that way. So I hope that that is clear. Are there any questions? Not necessarily related to this aspect, but in general. in stress analysis? Are there any questions? Because otherwise, it is just one way I'll go on solving problem. It will be a little dry. So anyway, if you have any questions, you please feel free to stop me and ask them midway. Okay. Yes, sir. Please go ahead. Okay, no problem. Yeah. Okay. Yeah, yeah. No problem. No problem. And anyway, I'll be sharing these videos also, so you can catch up collectively. And if you have any questions, you can bring them up as and when you get them. Okay. So 7. On solving a beam under pure bending using analytical method, taking plane stress assumption, one gets which of the following? So first, let us draw the beam that they are talking about. I'm Since it is plane stress assumption, I need not worry about the out of plane response. So I may as well confine my beam to this plane. So this is my beam. Now it says that the beam is subjected to pure bending. So let me take this beam and subject it to pure bending. What does that mean? It is subjected to a constant bending moment throughout. Let us call that M. Okay. So now, how will this get deformed? We know it will get deformed something like that. Something like that. So the top fiber will be in compression, the bottom fiber will be in tension. Okay. So now, at any point, if this is my neutral axis, at any point from the flexure formula, what is it that I know? I won't derive the flexure formula because that is already done in our strength of material course. You can just revisit that. So it says M by I Z essentially, I should say, with this as X, this as Y. So XY. So Z will be out of the plane of the paper. So IZ is nothing but minus sigma X by Y equals E by R or rho or whatever you take to represent the radius of curvature. So what we are able to see here is sigma X given a moment. Sigma X is nothing but minus M by Iz into Y. The section is not changing. The bending moment applied, I have applied is not changing. So essentially, this quantity, is a constant. So I can see that my sigma x is proportional to y. So it is having a linear variation. Now, what they are asking is, again, this is only talking about sigma x. Sigma y and tau xy comes out to be 0. Why? Tau xy is 0 because there is no shear. Sigma y again is 0 because there is no traction in the y direction. So essentially we have only one stress component, which is sigma x, which varies linearly. So if I have a line like that, it will vary linearly. This is compression, this is tension. That is the variation of sigma x about the neutral axis. So if I have to represent this stress state for plane stress, what does a stress tensor look like? Not Let me not say plane stress. In general, how do we populate a stress tensor? So this is sigma xx, sigma yy, sigma zz, sigma xy or tau xy. Let me say tau xy rather. And these are just symmetrical, so I'm not going to write them. Now, if I were to populate my stress tensor for this problem, I know from here, I know that sigma x is nothing but some constant into y. Sigma y is 0. Sigma tau xy is 0. So let me populate this for this problem. For this problem, I have this as minus m by Iz into y. So the first term is done. We have seen tau xy is 0 because there is no shear, it is 0. Sigma yy we know is 0 because there is no traction. Now, by virtue of this, by virtue of our plane stress, all the out of plane stresses are 0. So this is 0 and this is also 0. So this is my stress tensor essentially. So this is my stress tensor, which is uniaxial stress. Now let us go to strain. So how do we define strain? Strain is nothing but that stress by E minus mu by E trace of sigma I, something that big constitutive Hooke's law basically. So in plane, or rather, what are the strain components? How do we calculate the strain components? Essentially, we know epsilon xx is nothing but sigma xx by E minus mu sigma yy by E minus mu sigma zz by E. And this goes on cyclically. Yy is this quantity minus mu same thing will come here, and then epsilon zz is this minus mu. I'll just, or rather, let me write it this way. So this is the general Hooke's law for, I'm writing only normal stresses. Shear stresses are anyway decoupled from the normal stresses. Shear strains are also decoupled from the normal strains. So when shear stresses are 0, shear strains are also 0. So I'm not talking about shear strain. Let me talk about only normal strains. Now I can see due to plane stress, in the case of plane stress, I have sigma yy from my stress tensor. I know only sigma xx exists, other two are 0. So I can knock off the other two terms. So sigma yy is 0, sigma zz is 0. So I can see that because of the Poisson's effect, I still have non-zero quantities in yy and zz direction. So anyway, I suppose many of you knew this, but I'm just writing this for the sake of completeness. So what this implies is, for the case of a beam under pure bending using analytical methods, taking the plane stress assumption, we have a uniaxial stress state and a triaxial state of strain. Why triaxial? Because we have epsilon xx, yy and zz. We have strain in three directions because of the Poisson's effect. So I hope that that is clear. If there are any questions, please feel free to ask. Okay, fine. So let me move on to the next question. So with your present understanding of the experimental techniques, present understanding meaning whatever is covered in week 1, identify the problem along with the information given in the figure and the corresponding technique to obtain them. Now one thing we can readily see is something like that is given. This essentially represents the there is something called a master grating, and then there is a name to this grating also. That is master grating will be applied to the specimen, and this grating, test grating, I'll just clarify that and I'll mention it here. So let me just call it test grating as of now. So essentially, when we apply a master grating and then we view it with this, we'll get certain patterns because of interference. So this is essentially from the technique of Moire, which measures displacement components. So from here we can see, if we go through the lectures also, we'll see that whenever a grating is put in one direction, we essentially get the displacement perpendicular to that grating direction. So we can see that our gratings are like this. So we will be getting displacements along this direction. If the grating were actually like this, then we will be getting displacement along the vertical. So here we are sure that our grating is vertical. So the displacement, first of all, this is Moire. So Moire measures displacement. So in that displacement, due to this grating direction, I can see this is specific to U displacement along X, where I define X like that, Y like that, and Z like that. So I'm essentially having displacement along this direction. That is what I'm measuring with this grating. And from the very problem, we can see, let us see the options. Displacement information, and then slope and deflection. Since we are having a grating, we are talking about displacement only. So slope is not the answer. Now, deflection of a cantilever beam. Essentially, deflection, if we consider this to be the cantilever beam, deflection will be in the vertical direction. And since we have already deduced that this is in the x direction, this is not the answer. And from that very pattern, we can see that displacement information for a beam under pure bending using Moire. We know that pure bending is a symmetrical problem about the vertical as well as the horizontal. Whereas we don't see symmetry about this. About the vertical, we don't see symmetry. We only see symmetry about the horizontal. So it cannot be a beam under pure bending. So it is essentially a cantilever beam subject to a load at the end. So what I'm trying to say is you also look at the options and try to holistically reason out why certain options cannot be the answer based on symmetry arguments or based on the grating direction. So that is why it said whatever knowledge you have of the experimental technique and your background on the theory of elasticity and uh, strength of materials, you are expected to answer this. So what we are looking at is we have a cantilever beam that is clamped at one end, applied with a load on the other. This has one type of grating. So we have put a master grating over that cantilever beam, and then we have our test grating or whatever that term is. I'll write it clearly when I post this. It is it is mentioned in the lecture. So when we view it from that grating, we essentially see patterns. We will see these type of patterns, which represents the displacement in the direction perpendicular to that grating. So I hope that that is clear. Okay, so I'll move on to this question. Match the following. Choose the appropriate letters A, B, C, D, with A being this femur, B being this circular pattern, C being this cup, D being this. Now, before we go, we are able to see here certain patterns like this. I hope you are able to see. There, there is one. So there are patterns like this, which is getting formed due to interference. And this is what Moire patterns look like. Essentially here, when the light falls on this, it gets reflected and reinforced, and it leads to the formation of this shape. So why we are trying to see this is because this curved surface is responsible for the formation of this cusp, and which is called the method of caustics. Well, the principle is called caustics. Now, when we saw that a curved surface is able to bring this, when we take a body and apply load to it, and if it gets curved, and if we impinge certain controlled light over it, and obtain how it gets reflected on a screen or recording medium, then we can interpret such patterns which can be correlated to its curvature, out of plane displacement, and so on. So that is the essence behind this. Here, because there are two patterns, there is interference between these two, and we are able to see patterns. So here, what we do, if we take one type of one fan, this table fan's frame, there are two frames posed like this, and when this it is moving, it is creating this pattern. So you can consider the backside frame to be stuck to a specimen. The front frame is which you are holding in order to see it. And instead of the fan rotating, let that specimen bend or twist or something. That will also lead to that pattern's movement. And we will see interference pattern. So that is the principle behind Moire. And we saw this is nothing but our out of plane displacement. This looks like an oblong. Actually, it is a circle. It is some issue with the aspect ratio. This essentially is a circle only. And it is concentric at that. And here we are able to see again a very complex geometry. As we saw for the spanner, this is even more complex than the spanner. This is for a human femur. So naturally, analytical methods cannot capture this variation. So this either has to be handled numerically using numerical models or using experiments. So as we have seen, we have a jig from where we are applying the load, and this seems to be showing some patterns, some colors in some specific order. So we can see this is nothing but photoelasticity. This is from these patterns are from photoelasticity, much similar to what we saw uh, in the case of that spanner tightening a nut. Similar to that, we have patterns, not exactly same. I mean, as we load it, certain patterns, colorful patterns emerge. So that is what I meant. So displacement information. Which of these is displacement information? This, as we discussed in detail, D is the displacement of a clamped circular plate, the out of plane displacement of a clamped circular plate. So this is B, that is W displacement of a clamped circular plate subjected to central loading, so that I'll avoid to write. So the principle of caustics, as we saw, because of this curvature, it behaves like a lens which essentially reinforces the light in certain points, which leads to the formation of this pattern. Same thing we try to utilize in our mechanical stress analysis. So this is nothing but our C. Principle of Moire, it is straightforward to see that B and C are not the options, and A is essentially photoelasticity. So D, used for displacement measurement. The the concept of Moire is used for displacement measurement, and stress information is from photoelasticity A. What type of stress information? Essentially, we are getting sigma 1 minus sigma 2 equal to some constant. What this constant is and how this equation is derived, that we will see in the subsequent weeks when we get into deriving the principles and discussing the principles and deriving equations for photoelasticity. But for now, you can consider that it is giving contours of sigma 1 minus sigma 2. Contours means it is essentially line joining some parameter value. So as we vary k, we will be getting different patterns. That is the essence behind it. So are there any questions at this stage? Yes, yes, please. Yeah. Sir, you're not. Yeah. Yeah. Could you please repeat? I couldn't hear the first part of what you said. Yes, yes. Okay. Yeah. 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 Okay. Okay. No, it will get deformed like that, right? So the point goes like that. Yeah. Yes. V. Yeah. Exactly. Okay. Yeah. 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 Even in the case of a beam subjected to 4-point bending, there is U and V displacement, but we are essentially concerned only with one of the, because that is what is dominant. But essentially, displacement occurs in, if the entire beam had a V displacement, then it will be just, if the entire beam had only one V displacement, it will be a rigid body motion. The beam will be here, then the next moment it will be here. Because we are holding it and twisting it, so essentially each point will get mapped onto another plane, which won't be essentially a translation. It will be translation plus rotation, which will what will cause U also. And there is a closed form expression for U also. In the lecture, it is given the U displacement for V. Okay. Yeah, thank you. Thank you. So, which of the problem, which of the following problems a closed form solution is available? So directly we can take out spanner, tightening and nut, because we don't know a way to actually capture the geometry. So spanner doesn't have a clamped circular plate with a central load. This definitely has a closed form solution from plates and shells. That is theory of elasticity in polar coordinates when we see. Disk under diametral compression, we do have essentially how this problem is solved is it is a superposition of three separate problems. One is a problem of a semi-infinite plate with a theory of elasticity has a problem of a semi-infinite plate subjected to a point load. This is a semi-infinite plate. This, the solution for this plus one that is applied here plus a disk with radial tension. So these two essentially, this problem and this problem are celebrated problems that are solved in theory of elasticity. So happens that when we intelligently superimpose these, we get the equations for solving the disk under diametral compression. So this is possible using theory of elasticity. So a closed form solution is definitely available for this from theory of elasticity. And beam under 4-point bending we already know from our strength of materials. So this itself gives us the closed form solution at every point. So I hope that that is clear. Okay, so let us look at this question. The inner core of a rail cross section is removed due to the fact that due to which of the following is what is asked. Stress is distributed uniformly across the cross section. The inner core does not contribute to load sharing. The rail is subjected to bending. The stress varies linearly across the rail section. Now, if we see, let us consider a bar like this, and then we pull it on both the ends. Now let us say that both are subjected to P. I am trying to pull that bar. So if I were to take this, take a virtual cut. I just cut the section virtually, not physically. Just for the sake of my analysis, I cut this. And I know that when I'm pulling the bar, it is not translating here or there. It is still in static equilibrium. What does that imply? That there must be some stress that gets developed over this area, which balances out P. Now we know that when we are sufficiently far away from the loading end, sigma is constant over the cross section. That is integration of sigma over this dA gives me P. And area, we can actually see from here only we get sigma equal to P by A. So at each and every point across the depth, sigma is same. And this only happens in the case of uniaxial tension. Whereas a rail is subjected to bending because it is supported if this is the if we look at the cross section, that is the longitudinal section, I mean, it is supported like this. So when there is a load, when there is load applied like that, whatever that is. So essentially this beam, if we look at just this portion, if we look at this portion, this is subjected to bending, 3-point bending or 4-point bending, whatever that is. It will keep changing as the vehicle moves. So this is essentially subjected to bending. And in the case of bending, this sigma, it cannot have a constant variation, that is for sure. It might not have a linear variation in the case shear is present, because the flexure formula is only valid for when shear is absent, that is, it is subjected to constant bending moment. Whereas it might not necessarily be subjected to constant bending moment, in which case sigma x variation also might not be linear. So our rail is definitely subjected to bending, and it does not have a uniform stress state. So in general, for bending of beams, what is it that we do? We generally neglect the non-dominant quantities, which are nothing but shear in this case. In the case of bending, shear is very less. That is why even for cantilever beam, we apply the flexure formula. So we consider it that it is varying linearly, and the inner core does not contribute. So now let us say that this is the cross section of the beam. What I mean to say is I take a cut here and then I try to view it like this. So my rail is something like that. Something like that. So in that, if I see, my stress variation is like that. Of course, this will be more bulbous and this will be thinner. So my neutral axis will be somewhere around here. It will be pulled up because of more area distribution, but I'm considering a general I section for the sake of simplicity. So now I can see that this portion, what is the stress it is taking? It is much less as compared to the far ends. So generally only flanges, in an I section, only flanges are responsible for taking the bending. Web as such doesn't take bending, it takes only shear. So the inner core doesn't participate much in load sharing. Then we might ask, why not we remove this totally? Why don't we have just flanges? Essentially, if we have to make a component, it has to be connected with something. And if this is totally redundant, if it is not participating in load sharing, why don't we make it much less, much thinner? So there is a certain problem that arises when we make the web more and more thin. Essentially, we saw that it is subjected to shear. So there is a chance of web buckling that can take place. So to avoid that, we are constrained to keep certain width for the web in that section. Nonetheless, it does not contribute in load sharing. Why? Because the most dominant load in the case of rail is our bending load, and that is not the core is not contributing towards taking that. It's only the flanges, the bulbous head, and the bottom flange that is taking that load. Is it clear? Any questions? Okay. So let us look at the next question. Which of the following are true regarding functionally graded materials? So till now, we have seen generally when we take, even if I were to take that spanner problem, generally what will we do? We will assume that at each and every point, let us say this is the sheet. This is, okay, let me explain it this way. Let us say that this is a metal sheet that I have. Now I cut out a component like this. and then I cut a component like that, and then I cut a component like this. Now, it is not necessary that the sheet has same elastic properties in all the directions. But in order to proceed with the analysis, I have to make certain assumptions. So we make an assumption that the elastic properties along this direction, elastic properties along this direction, and the properties along this direction are the same. So that is the assumption of isotropy. Now, let us say that this is made of some metal, some alloy maybe. The composition at this point may not be the composition at this point. The composition at all these points could be different. That is, within the same component, at different points, I might have different compositions of the material, which might lead to difference in the difference in the properties in general, mechanical properties in general. Even mass, for that matter, might not be uniformly distributed. So I make another assumption that the material is homogeneous. That is, within the component, no matter which point I pick, it is of the same composition. So that is my assumption of homogeneity, that the material is homogeneous. So a tooth, okay, that is a giveaway. Anyway, functionally graded materials are those graded material. So naturally, we are talking about some material. I need not even explain that. What is graded? It has a variation of properties. Within the same material, I have a variation of properties along different directions. And it is functionally graded. Yes, sir. Yeah, please go ahead. Yeah. No, sir, it could be other properties also. Since we are only talking about mechanical stresses and strains, I am confining my attention to mechanical properties. It could have yes, it could have dielectric properties that could be different, magnetic properties that could be different. But as far as we are in this course, I'm confining my attention to the mechanical response. Yeah, you were saying something, please. Okay, okay, yes. Yeah, no, as you said, even in SS, there are so many variations that are coming, but that is for each and every batch. It is not, for example, if I were to buy an SS piece, let us say, if I buy it for two different compositions, each of that batch will have that composition. It is not varying through that space of that batch. For example, if I buy this sheet, the manufacturer, if he says that properties at this point in that sheet and properties at that point in that sheet are same, that is what they will at least say. If those itself vary from point to point, and if it is by design that it actually does vary, in essence, it is very, if unless it is produced in a very controlled environment, there will be slight deviations here and there due to its yes, yes, but it is negligible. Whereas why we are saying functionally graded, this is by design. That is, we want this to be like this. For example, if we were to take that same problem here, let us say we want the material to be very strong here because it is taking a high amount of stress. We don't want the material to be very strong here because we can do away with less amount of stress because it is subjected only to less amount of stress. So if I were to design this piece of this material in such a way that as I move away from its center, it gets stronger, then that is I am designing it that way. So there is a functionality behind that, and I want the material property to be graded in that particular way. So that is what we mean by functionally graded material. Essentially, if we look at our femur, our bone and our teeth, they are very soft, hard on the outside. And if we go in and check the properties, it will be very, very soft because the nerve ending have to, it is connected to the nerves. So it has this inbuilt quality which has come about by evolution. So there are natural materials that are functionally graded, but to analyze these, it is a Herculean task to analyze and design these. So that is under the purview of research, extensive research on how to, create functionally graded materials by blending and how to have control over it. So there are many such research is taking place. So when we say functionally graded, it is definitely not homogeneous because, yeah, from point to point, the material has variation in properties, which is by design, not by chance or by accident, or it is not inevitable. We have put it there. They have varying properties within the volume of the material. Essentially, I was talking only about a sheet. If you take the out of plane variation also, we will come to the volume also. Tooth and bone are examples of functionally graded materials. Because we spoke of the tooth, if we look at the bone marrow, even the professor mentions this couple of times in the lecture, the bone marrow is responsible for the production of hemoglobin, blood. So that has to be very soft, whereas its entire strength comes from the outer core, which has to take bending and twisting. And we know from bending and twisting that the strength is directly proportional to the moment of inertia. For any section, for a particular section, it can be characterized by two things. One is the area, one is the distribution of the area, which is what is nothing but the moment of inertia. So now, if I have a section, the farther I place the material from its centroid, the greater the strength it has in terms of bending and twisting. So that is how a bone also has evolved. It has a hard core, it has a hard outer surface, which is very strong, and as we go in, it becomes soft. So it derives its strength based on the outer periphery of the bone. I hope I'm making sense. Anyway, I'll move on. Experimental methods provide direct information. In this context, which of the following statements are false? Just false is what is being asked. Majority of the optical techniques provide whole field solution. Generally, what is the principle behind optical techniques? That we impinge a controlled light on the specimen, either that can reflect or refract or undergo some changes, and we will essentially try to capture the output based on a screen or recording medium, and we'll try to observe and interpret the output. So when we impinge that light, we don't have control that we will impinge it only on one point. We generally impinge it on the model, and whatever response we get is the response of the entire model that is exposed to that light. So in general, optical techniques are whole field, give whole field solutions only. It gives whole field solution, but need not be closed form. That is, for every point, it might give a particular type of information like displacement or stress, but it not need not give all the three: strain, stress, and displacement. So I suppose that is clear. So this is true, but the question asks which is false. So A is false from the context of this question. Strain gauge is used to obtain a closed form solution. Essentially, strain gauge measures a component of strain alone. It doesn't give us displacement, or we have to work our way back to stresses. And in order to get from uh, strain to displacement, we have to invoke our compatibility conditions. So this does not give us a closed form solution. A single experimental technique can provide all stress, strain, and displacement information. As we saw, in numerical methods, once you model the once you make a numerical model and you have verified it, at the click of a button, you can get the field parameters, namely the stresses, stress being the six stress components. You can get the six strain components and the three displacement components as well. But experimental techniques, they employ a certain physics which has been observed, and we try to interpret the answers for that. For example, as we saw here, in this particular case, we saw that certain materials have this property of stress induced by refringence. So when we uh, exert, that is when we exert them to applied loads, then they develop stresses. It induces stresses inside, which manifests itself in the form of these fringe patterns. So there is a physics behind it. Similarly, we saw this interference that is happening. So we have employed this technique and developed it as Moire in order to measure displacement. So each and every technique is based on some physics, and there is nothing that can capture all the three at once. So experimental techniques are very specialized, but nonetheless very useful because, sorry, this let me not confuse by putting ticks and crosses. This is true. This is false. Single experimental technique cannot capture everything. So essentially, we have to find the suitable technique for what response we are trying to study. So that is how that and economics and so many precision, so many other things go into selecting the technique. And Moire technique, as we saw, it measures displacement and not stress. So essentially, this is false. So from the perspective of the question, which are these are false? B, C, D are false. So I hope that that is clear. So let us move on to this question. It says match the following techniques with the information provided. Photoelasticity, geometric moire, moire interferometry, holography, and brittle coating. So essentially, what is the difference between these two, geometric moire and moire interferometry is interferometry has an extremely fine grating. We saw one grating. We saw a fan. We saw this fan. Now we can safely say that the distance between those two, uh, we have sort of spokes like these. So the distance between these two spokes will be of the order of centimeters. We can say maybe 1 centimeter or half a centimeter, varying throughout. So in the case of geometric moire, in 1 centimeter, we may have several lines. In 1 millimeter, we may have couple of lines in order to carry out the experiment. Whereas when there are sophisticated technologies which can manufacture gratings, gratings meaning that patterns with those lines. Those lines can be so dense that within a millimeter they are able to make hundreds of lines. It's a very sophisticated technology. So when we have such gratings which are very fine, we need special techniques in order to interpret the results also. So that comes under Moire interferometry. When the gratings are reasonably coarse as compared to them, it comes under the category of geometric moire. Both have different precision levels also in order to measure the displacement. So that is one difference between these two. So let us see A, B, C, and D. So clearly we know photoelasticity gives us principal stress strain difference. Now it begs the question, till now we were talking about principal stress difference only. Then where does this principal strain difference come in? Now photoelasticity has many variants. One is called a transmission photoelasticity. Of course, these will be covered in detail when we go into when we go further in the course. But I'm just giving you a brief of that. Another is called reflection photoelasticity. This basically measures sigma 1 minus sigma 2. This measures epsilon 1 minus epsilon 2. What is epsilon 1? It is the maximum principal strain. So one is for transparent medium. The other is for any opaque medium over which we will coat something that has that property. We will see more about this when we get to that module. But we can also measure principal strain with this. So essentially, photoelasticity measures principal stress or strain difference. Okay. Now, geometric moire, we know it measures out in and out of plane displacement. Moire in general measures in and out of plane displacements. But if we look at the from the options perspective, geometric moire, they're saying it can either measure principal stress strain difference or in and out of plane displacement. So it would have to be in and out of plane displacement. And now let us say that we have 2 points, and then these 2 points deform to here. It was connected using a line. It is like this. So if its length is L, this is my V displacement and this is L. So how is strain defined? Strain is nothing but the gradient of displacement. So essentially strain will be V by L. Strain in one particular direction, I'm saying. I picked a poor example. What I meant to say is if it was lengthwise, if you were to take it lengthwise, so strain is nothing but change in length upon original length. That change in length can be decomposed into 3 components. So naturally, we can get strain from there. The thing is, as we make finer and finer measurements on displacement, our strain calculations also will have certain amount of accuracy because numerical differentiation or differentiation in general, no, numerical differentiation is more error prone than numerical integration. So if our measurement of displacement is poor, then when we differentiate it, our measurement of strain, our estimation of strain will be poorer than our measurement of displacement. So a method that can have high accuracy on displacement measurement can provide reasonably good strain measurement. So in that sense, if we compare these two, we saw that Moire interferometry employs a grating that is extremely fine, which leads to high precision measurement of displacement, which translates to a high, reasonably precise measurement of strains. So in that case, the strain over the domain can be measured using strain. In that case, strain over the entire domain. Now, there is two things to be kept in mind. This says component of strain over the entire domain, component of stress at a point. Now we will see component of stress as a point is generally measured using strain gauges. Strain gauges are employed generally to measure the component of strain at a point. And we saw this is a optical technique. So this will give us the whole field solution. So over the domain, we can measure the component of strain depending on which direction our grating is. I hope that is clear. Excuse me. So Moire interferometry leads to the measurement of component of strain over the entire domain. Then let us come to brittle coating first. Now what essentially is a brittle coating? That we have some component. Let us say we have a component which is subjected to some traction and some constraint. So this is stressed. And in general, we know that brittle, from our theories of failure also, we know that brittle components fail in tension. From maximum principal stress, they fail. So if I coat this material over with some kind of a coating which is very brittle in nature, and let me consider one point here. Let me consider this point here and then draw the state of stress at that point. So this will again have sigma x, sigma y. I'm just figuratively drawing these. These need not be tension or compression. It will depend on the type of loading and the point that we are considering. Let us say that the stress state is like this. So when a brittle material is stressed like this, because the brittle material is coated on the test specimen, and we are loading, which is leading to a stress state like this. Essentially, this can be decomposed into some plane where we have sigma 1 and let us say sigma 2, like that. Again, it can be tensile or compressive. I'm just telling you one example. So what we did, we took a specimen, test specimen, we coated it with a brittle coating, and then we loaded it. At this point, the state of stress was like this, which can be decomposed like that. Since the material is brittle, it will fail by maximum principal stress theory. So if maximum principal stress is tensile like that, essentially I'll have a crack that gets formed in the coating like that. I hope that is clear. If the principal stress was in some other direction, I'll have a crack perpendicular to that direction. So at this point, what has this technique readily given me? It has given me a crack using which I can directly identify the maximum principal stress direction and the minimum principal stress direction, because both are perpendicular, orthogonal to each other. So at once, by analyzing this point, it would have developed a crack like that. And at each and every point at that crack, I know what is the maximum principal stress direction and the minimum principal stress direction. So essentially, brittle coating gives me principal stress direction. This is the advantage of brittle coating. And we will see as we go about in the course that how this can be advantageously used along with strain gauges in order to uh, optimize our experimentation. So E is 1. Oh, I didn't write that. E is 1. So then halography would have to be any one of these following. E is 1. So from here we are deducing that this gives out of plane displacement. Halography can also be used to get the sum of principal stresses, but both have different arrangements that are needed. In any case, in this way, you can approach the problem from what you know and at least try to deduce what could be the answer. In any case, we can go into each and every method that is mentioned here and try to understand what is the physics and how it tries to measure, which will be taken up in the subsequent weeks. So anyway, so I have run out of questions and we have nearly run out of time. So we'll end it by 8. So based on what we have discussed, if there are any questions, you please feel free to ask. Was it clear, the discussion? Are there any questions? Anything that is not clear? Anything you want me to explain again? Uh, am I going at a comfortable pace for you, or should I slow down? Yes, please. Go ahead. Yeah. Okay, fine. Thank you. Yeah, that's all right. Okay, it's clear. Yes. Yeah. Yes. Yeah. Yeah. In the subsequent weeks, if you look at the lectures, at least a schematic of the principle is explained. Naturally, because there are so many different techniques, and in fact, the techniques are also developing over time. Now we have something called digital image correlation that was not there earlier for displacement measurements. So techniques are also evolving and getting new. We are getting new techniques by the day. So naturally, to accommodate each and every technique into the course, it's a big challenge. But professor has done it in a very professional manner. In that, at least for the methods where he has not gone very deep, he has at least given an overview, a decent overview with the schematics and how it is measured. What are the merits, demerits, what is the precision level? All these have been covered. But as we move on towards week four and onwards, we will be mainly looking at photoelasticity, the different variants of photoelasticity, and then we look at brittle coatings, then strain gauges, and we'll end with that. So the emphasis will be on this, but nonetheless, he has given an exhaustive introduction on all the techniques that have been discussed here. So you should be able to, it'll at least give you a solid groundwork to proceed forward. Okay, yeah, yeah, all right. Okay, so someone had, yeah, thank you. Mr. Praveen, okay, it is clear. Okay, thank you very much. Okay, very well. So in that case, I don't have anything more to add as of now. So if there are no further questions, I'd call it a day, and I'll see you people in on next Monday, same time 6 to 8. Throughout the semester, it will be the same link, and I'll be uploading this video very soon, and those links will be shared with you in due course of time on the Swayam portal page. So you can refer back to the recording in case you missed it or you're not able to attend. And if there are any questions, please feel free to approach the forum or note them down and we can discuss it in the next session. So thank you. Thank you with that. Thank you for attending. Thank you.